Okay, so hello everybody. Now we will move from pure theory to pure experimental. I don't know why I'm here in, in theories in the air, but it's okay. So I work with conical refraction. It's an optical phenomenon, and well, I guess that any of you know nothing about it, so I will give you some key points, okay? Conical refraction occurs when we send a laser beam along the optic axis of a biaxial crystal, and in this case, the Gaussian beam, for instance, this circle of here, is transformed into a bright ring, into a light ring after a biaxial crystal, okay? And this light ring has very peculiar characteristics. One characteristic, for instance, is that if we send a linearly polarized beam, instead of having this light ring, what we have is like a croissant pattern with a point of null intensity in one of these sectors. Then, another characteristic is the light polarization distribution along the ring. And it is well known that there are rings, light rings with pure radial or pure azimuthal polarization distributions, but we have here, it's a combination. We have that every pair of opposite points have orthogonal polarizations, and this polarization distribution is rotating along the ring. Then another interesting thing of this conical refraction is that the transformation is completely reversible, so that if we place another biaxial crystal after the first one, but with opposite orientations, we will combine totally the input beam, and it doesn't depend on the shade of this beam. And what we do is to try to explode at most this phenomenon in different applications. I will show you some of them, okay? So one application was the creation of a conical refraction laser. And this laser showed that to be with a very high efficiency, very high power and high brightness, and very curious characteristic is that it has at the same time Gaussian profile and this ring profile. So we have these two beams, one from the top part and the other for the bottom part. No pasa. Pasó. Se pasó demasiado. Okay, then when we see this light ring, what we think is about optical tweezers, okay? And a group from Dublin has been able to, using these linearly polarized beams, to catch a particle from this, in this dark region and to rotate it by just turning the light polarization distribution along the ring. I have a video here. The good thing of that is that it's very easy to, not working. It's very easy to do these things because you only need a crystal and a polarization, a linear polarizer to rotate these particles, and it's an easy tool for optical tweezers. Then another application that we have found is for free space optical communications. In this case, what we did is to select some parts of the conical refraction ring and combine them with another biaxial crystal, with a second biaxial crystal. Then this combined beam can travel in free space, let's see, kilometers, and then a third biaxial crystal decompose again these sectors of here that, if they are modulated in time, are communication channels. And finally, one of the research lines more active that we have in our laboratory is to play with the ratio between the ring radius and the waves of the input beam to generate this kind of profiles that you can see in this part of here, and also play with different multiple crystals, one placed after the other, and generate this ring pattern. Why? Because the general topic of my master thesis, my PhD thesis, is to trap neutral atoms and Bose-Einstein condensators in these kind of rings and also in these geometries. And the reason is to build an easy tool and cheap and very controllable tool to make artificial atoms or mesoscopic atoms, for atom interferometry, for adding periodic boundary conditions for Bose-Einstein condensators, for instance, also to study entanglement between coupled rings, and so on. And this is what we do. Thank you very much.